In this video, we'll talk about section 4.6, about the change of basis. So sometimes one basis is more convenient than another, and that's why we'll need to change our basis. So we've seen an instance of that to some extent. So we begin with a vector like -2, 4, and in the standard basis, that's the basis consisting of e1 and e2, the vector -2, 4 is simply -2 times e1 plus 4 times e2, and we say that the coordinates of v, this vector v, -2, 4, relative to the standard basis e1, e2, is -2, 4, written as a column vector. Now, what if we change our basis? So suppose we have a different basis, v1 being 2, 1, v2 being 3, 2. These two vectors form another basis of R2, and we've seen in a previous video that this vector v given by -2, 4 is a different linear combination of v1 and v2, namely -16 v1 plus 10 v2. To recall how I found these numbers -16 and 10, I need to solve this system of linear equations. That comes up taking the vector v1 written as a column vector, replacing it or making it the first column of this matrix here, and similarly for the second basis vector, putting that as the second column. Then I want to find numbers c1 and c2, so that when I do this matrix multiplication, I get the vector v -2, 4. And then here's the sage math code for solving or finding c1 and c2. We're use the solve right command because the unknowns are on the right of this matrix A, and we get -16 and 10 for C1 and C2. So we say that the coordinates of V relative to this other basis, V1 and V2, is -16 and 10. Note that that's different from the original vector V, which was -2, 4. These are the coordinates relative to the standard basis, but here's the coordinates relative to a different basis, v1 and v2. In this section, we're going to answer the following question. Suppose V is a two-dimensional vector space, or actually any dimensional, and B is a basis consisting of two vectors v1 and v2, and then suppose we have another basis, v prime, which is v1 primed and v2 primed. That's our new basis. And suppose v is a vector in V, and the coordinates of V relative to the basis B are given by some numbers k1 and k2. And these are the coordinates in the old basis, the original basis B. What does that mean? That means the vector V is a linear combination of v1 and v2 given by the coordinates. And the question we want to answer is, what are the coordinates of V in this new basis B primed, which is consisting of these other vectors v1 primed and v2 primed? In other words, we have to write V as some linear combination, unknown right now, of v1 primed and v2 primed. And so the trick is to express v1 in terms of v1 primed and v2 primed, and v2 in terms of v1 primed and v2 primed. Remember, the information that's given is v1, v2, v1 prime, v2 prime. That's all given to us in specific examples. And okay, so then because v1 primed and v2 primed form a basis, by definition of basis, that means that every vector can be written as a linear combination of v1 primed and v2 primed. In particular, v1 can be written as a linear combination of v1 primed and v2 primed. So there are some numbers a and b for which this equation holds. And similarly, there are some numbers c and d for which this equation holds. We will be in principle able to find these numbers. Right now, we're just imagining actually that we can find them. And so what does that, well, what do we do with that? Well, we know that V is K1 times V1 plus K2 times V2. That's because K1 and K2 were the coordinates of our vector V with respect to their old basis. And then replacing V1 by its linear combination in terms of the new basis, that's what I've done here, likewise for V2, and then doing the algebra and collecting v1 primed and v2 primed, I see that the vector v is this multiple of v1 primed plus this other multiple of v2 primed. Because how did I get these numbers? Well, v1 is k1 times a, has a coefficient of k1 times a from here, and then on this side, v1 has a coefficient of k2 times c. So k1 and a are numbers, k2 and c are numbers, the v1 prime and v2 prime are vectors. So this here is a number in practice. Okay, and then writing the answer in this line as in terms of matrix form, we get k1 primed. If I denote this as a new coordinate, namely it's the coordinate of v in the new basis, we get that k1 primed is a times k1 plus c times k2, and similarly k2 primed is b times k1 plus d times k2. And so this is the answer to our question of, if you're given the old coordinates, or the coordinates in the old basis, how do you find the coordinates in the new basis? Well, you multiply by this matrix here. And so the key point will be how to find this matrix. And this matrix here is just expressing the old basis vector, each vector of the old basis in terms of the vectors of the new basis. And we call this matrix the change of basis matrix and denote it P from when you're changing your basis from B to B primed. Let's do an example. Suppose our first basis B is consisting of these vectors 2, 2, and 4, negative 1. Those are called U1 and U2 in this example. And let B prime, our new basis, be given by these two vectors. And we want to find the transition matrix, or the change of basis matrix, from B to B primed. And so what we do is we take the first vector of our old basis and express it as a linear combination of the new basis, the vectors in the new basis. And doing that means solving this equation down here, because u1 is 2, 2, and we want it to be a times 1, 3 plus b times negative 1, 1. So we have to find out what a and b are. And we've seen that this amounts to this matrix multiplication. And so we can do a couple things. One, we could form the augmented matrix and row reduce, or we could take the inverse of this matrix and multiply both sides of this equation by the inverse on the left. So I've done the second suggestion down here. So I take my matrix A and form the inverse. Because this is a 2 by 2 matrix, there's a simple formula for the inverse. It says take 1 over the determinant, and then take the diagonal elements, switch them. So my new diagonal elements are negative 1 and 1. And then negate the off diagonal elements. Okay, and then down here I've computed the determinant. 1 times negative 1 is negative 1. Subtracting off a negative 3 turns into plus 3. Okay, so then I multiply both sides of the equation a times ab equals 2. I have 2, 2. So here's 2, 2. Here's a times ab. And then I multiply it on the left by a inverse. The a inverse times a turn into the identity matrix. So all I'm left here with is ab. And then on the left-hand side, I just have to do the arithmetic. So I get, I've dropped a negative sign there. Okay, so I get 2 times negative 1 is negative 2. 2 times 1 is 2. Add them, I get 0. And then 2 times negative 3 is negative 6. 2 times 1 is 2. And then add them, get negative 4. And this 1/2, that's a scalar. And so that multiplies each entry of the matrix. 1/2 times 0 is 0. 1/2 times negative 4 is negative 2. So that's my answer, that a is equal to 0, b is equal to negative 2. Well, that's going to be the first column. We still have to find the second column, but our first column is ab of 0, negative 2. Next, I'm going to just, for the sake of it, just do the other way, form the augmented matrix. Here's our matrix A, and then here's the augmented matrix. We usually have the 2 out over here, but okay, and then just row reduce. Now here's the row reduction process. I won't go through it, but the point is that we get the same answer. A is equal to 0, B is equal to 2. Now to find the second column, we just proceed the same way. Express our second old basis vector u2 as a linear combination of the new basis vectors. So we want u2 is some combination, C and D, of the new basis vectors u1 primed and u2 primed. So the vector u2 is given to us as 4, -1, and these again are our new basis vectors. And we could either row reduce again or use the fact that we've now know the inverse, because the matrix A is the exact same matrix in the first step. And so all we have to do is multiply that matrix, the inverse, by 4, -1. Here I've just done the row reduction process in any case. Again, I won't go through it. Here's the inverse of the matrix, and then I multiply A inverse times the vector 4, -1, and I do the arithmetic and get -5/12, -13/2. And so that's going to be our second column of the change of basis matrix. Now, a little bit of a shortcut is to combine the two steps in one step. And so write the columns of the new basis here, the columns of the old basis here, and then row reduce simultaneously. You can quickly do this in Sage. Here's the code on the right, and use the reduce row echelon form method. And here is the change of basis matrix that we found.